Graphs.
Thank you, Gary. Thank you for coming back from lunch, and hope the talk will keep you entertained for after lunch. So I wanted to talk about some work which I've been doing for several years and is still in flux on trying to make sense of what it means to analyze graphs at different scales. And the title makes this perhaps not so fortunate in English pun between off and on, because I would like to talk both about how you look at a graph and you try to find representations of that graph at different scales, but at the same time what it means to look at functions on the graph and look at them at different scales. And it turns out that, at least in our approach, these two questions are very related to each other, and answering one answers the other one as well. And there hasn't been a lot of talk yet about multiscale. My background is actually in harmonic analysis and a little bit in geometric measure theory, where there is a long tradition in doing things in a multiscale fashion to understand objects, which are complicated and have different levels of uncertainty at different scales. And this is very popular also in image processing. Think about the analysis of sounds and of images. You analyze those objects by looking at them at multiple scales. And if you want to perform tasks such as denoising or other, or estimation, also in machine learning tasks, it seems very fruitful to look at these objects at multiple scales, where these different scales really should be handled differently or contain different types of information. And here is a list of examples where multiscale analysis has been fundamental. There has been the whole sort of in signal processing, the whole revolution due to wavelets about 35 years ago now. And its consequences in multiscale analysis and multiscale algorithms in a variety of disciplines. Similar things have happened in geometric measure theory, where instead of analyzing a function or a signal at multiple scales, you analyze a geometric object. For example, in the cases that I'm interested in, you analyze a point cloud by looking at it at different scales. And then there are many constructions in machine learning where, and of course also in spatial statistics, at least in the low-dimensional case, where you look at an object and you compute statistics at multiple scales, and you use all of them to make to construct an estimator for the object of interest. So what I would like to discuss today is some ways of trying to bring these ideas from multiscale analysis to the realm of graphs, which are usually thought, or very often thought, or maybe traditionally thought, as combinatorial finite objects. Well, the thing is that many of the graphs that arise nowadays are very, very large, and perhaps too large to handle, either in the computational sense, or in the sense that the fine scale information that is contained in these graphs is very noisy, and so the finest scale is not necessarily the scale that is most informative for any specific task. And so I would like, to talk about how to reduce in a meaningful way the size of large graphs by compressing them at multiple scales. I would like to use this sort of notion to perhaps make new suggestions for how to compare graphs. We're often interested in comparing different graphs. Both could be different realizations of a random graph. It could be a graph that changes in time. And the most classical notions of graph comparison, such as graph isomorphism, just is not very well suited for applications where, for example, the number of nodes in these graphs changes all the time. And so I think there is a need for more robust notions of distances between these discrete objects. And finally, there is always noise. For example, in the way we're sampling the vertices of a social network or of a graph, how we assign weights to the edges in these networks. And so, again, the finest scale in this graph might not be the most informative one, and we should have a way of somehow being able to convolve this noise out or average it out in a way which is consistent with the graph structure. So, as I mentioned at the very beginning, there are going to be two separate tasks, one that are going to be analyzed together. One is a multiscale analysis of graphs, where we start with a large graph and we compress it in multiple scales. And a sort of a dual aspect, this I guess was mentioned at the very beginning by Misha this morning, that sort of taking a dual point of view when you look at functions on the graphs can be a very helpful point of view. Well, you can look at functions on a graph and ask, well, how should I be doing multiscale averages of these functions? How do you do that by respecting the graph structure? And so we would like to do that as well, and in fact we will be doing both things at the same time. The most fundamental object that we're going to use is the random walk on a weighted graph. So this talk is going to be in the setting of weighted graphs, which are not directed, albeit most of the things that I'm going to discuss go over to the directed case, at least algorithmically, while theoretically there are still open questions about some parts of the construction that I'm going to discuss. So I'm going to restrict myself to the undirected weighted graph case. And so we have a matrix of vertices, we have weights W, n is going to be the number of vertices, and so W is an n by n matrix, which I will think of as being very large and also very sparse. So the total number of non-zero entries in W might be order n or order n log n. And one can define, as I'm sure most of you are familiar with this, with a random walk on the graph. That's that matrix P, which is just a matrix which is also n by n, and Pij describes the probability of jumping from vertex I to vertex j. We would like that to be proportional to the weight, Wij. Think of Wij as a similarity between vertex I and vertex j, so you would like the probability of jumping from I to j to be proportional to that, and the constant of proportionality that makes P a raw stochastic matrix is this inverse degree matrix, D inverse. D is the degree matrix whose high I entry is the degree of vertex I, so the sum of the weights of the edges attached to vertex I. So some people like to work with the random walk matrix P. Some other people like to make the observation that this P is typically non-symmetric, even if W is. On the other hand, it's conjugate to a symmetric matrix T, simply by multiplying by square root of D and inverse square root of D on the other side. And so P and T share eigenvalues and pretty much eigenvectors up to multiplication by D of the square root of D. Other people still prefer to talk about the normalized Laplacian, that's just 1 minus T, so similar spectrum and eigenvectors. And yet other people about the heat kernel on a graph, where you pick a continuous time parameter T and you look at the fundamental solution of the continuous time discrete space heat equation of the graph. And I will be mostly using T, albeit all these objects are related to each other. I'm going to call lambda I the eigenvalues of T, so they start from 1 and they decrease. And I'm going to call phi I the corresponding eigenvectors. And because T is symmetric, these are all real. And a very traditional method that people have been using to embed a graph into Euclidean space, and that has already been discussed several times this morning, in particular in spectral clustering, is the map that takes every vertex x of G to the m-dimensional vector, where m is a parameter that is fixed, m equal to 2 in many cases, where you evaluate the first m eigenvectors of T, or of the Laplacian, at the point x. And one of the most, I guess, successful applications of this has been to spectral clustering. Now, this is a comment so sometimes we are given a graph to start with. Some other times we construct these graphs. And this is actually, I've started getting interested in graphs, where you start with data which is actually Euclidean data in RD, and you define some local similarity functions between these data points, for example, by using a kernel such as the Gaussian kernel. And then your graph has vertices given by the data points and connections which have similarities given by this W matrix. But we will not be doing this in this talk. We will usually start from the graph as given to us. And so it might not come at all from realization of this construction at the bottom. So again, most of us are familiar with the properties of random walk. Just let me summarize some of the ones that I'm going to need throughout the talk. So I'm often going to think about P to the Txy, which represents the probability of going from x to y in T steps, as a sort of, if you take y as a variable, I think of it as a bump on the graph, a probability bump, centered at x and with a standard deviation, quote unquote, T. If we were in Euclidean space, of course, this would be a standard heat kernel looking object. On a graph, it can be a little bit more complicated. I already said that P and T are similar, which helps with the spectral theory. And also computationally, we should think of P and T as being very large and sparse. So the first thing that I'm going to do is use these random walks to introduce a multiscale analysis on the graphs. And later on, I'm going to use the multiscale analysis to define distances between graphs and look at the case where graphs change in time and measure how much they change in time at these different scales. So how do we do compression of these graphs? Well, I would like to produce a scale of graphs. If the original graph is G or X, I'm going to produce coarser versions of it, which I can call GJ or XJs. And every point of the graph scale J that I'm going to construct, it can be thought of as a probability distribution of the original graph, localized at some point. and it's going to be a probability distribution with quote-unquote diameter of a support about 2 to the j. So this is what the graph of the vertices of this graph at scale j are going to be. I'm also going to give weights to edges and weights on this graph at scale j. And I'm going to obtain those by looking at the random walk on the original graph at scale 2 to the j. And I'm going to compress it and represent it by one step of the random walk at scale j. So at scale j, we will have a list of vertices, each of which is a probability distribution of the original graph, and a rule for taking one step of the random walk at the scale j. And that one step of the random walk at scale j will correspond to taking 2 to the j steps of the random walk on the original graph. So the time of the random walk is going to be the parameter that is going to control the scales in these graphs. And then we will also be constructing basis functions on the graph associated with this compression scheme. Now, compressing a graph might sound like a cool idea, and there are many ways of doing that. The question is, what does it mean to have a consistent or faithful compression of these graphs? And so that the graph at scale j is really a compressed representation of the original graph that preserves some kind of information. So the definition that we give for this preservation of information is the following. We say, if you start with a function f on the original graph, and you diffuse it by 2 to the j plus 1 steps, that's going to be a blurred version of the function f, because t to the j plus 1 is diffusing the values of f up to time t equal 2 to the j plus 1. Well, that's going to be a very smooth function. Well, you can compute that smooth function in a different way. You can start with your function f. You can send it up to this graph at scale j. That's going to be a much smaller graph. You can diffuse one time at the scale j and go back. The results of these two operations is going to be, up to a precision epsilon, which is the only parameter in the constructor, is going to be the same. So the graph at scale j is really capturing all the information that there is for random walks at time scale 2 to the j plus 1 on the original graph. That's our notion of consistency and what we mean by saying that our compression is consistent with the structure of the original graph. And I'm going to go over this more in detail, but that's sort of the idea. So why should this be possible? Why should it be possible at all to compress a graph according to this criterion? Well, the idea is that if you look at the spectrum of t, it starts from 1 and it typically decays at a certain rate. By the way, I think there are many open research questions about what this rate exactly is. We understand that very well when the graph is a geometric graph, so it comes from a point cloud using constructions similar to the ones that I mentioned before. But in general, I think there are a lot of things which are not understood about the behavior of the spectrum of t for high frequency eigenvalues. And well, so if you look at the spectrum of t, it decays. So if you ask, well, I fix a certain precision epsilon, here I fix epsilon kind of large, like 0.1, then I don't need the whole spectrum in order to capture my operator t up to precision epsilon. I could compute, for example, the SVD of t, or compute the eigenvalues and eigenvector of the operator t, and stop at this stage of the spectrum. And I will obtain about maybe 17 eigenvalues and corresponding eigenvectors, and these eigenvectors span the range of t up to precision epsilon. And then if I apply to the range of t the operator t squared, I'm going to look at the spectrum of t cubed. Well, that decays even faster, and so there is an even smaller set of eigenvectors that span a subspace, which effectively up to precision epsilon spans the range of t cubed. And so I could keep going, obtaining a chain of included subspaces. And well, there is a canonical basis for those subspaces given by the eigenvectors of t, but I don't like those eigenvectors because they're typically non-local. I would like to obtain bases for subspaces like this, which are made of local functions, not of eigenvectors. And so the name of the game would be aiming to get this nested sequence of subspaces, which get smaller and smaller and capture lower frequency information for functions on the graph, and seek a localized set of basis functions for those subspaces.
How do you measure the quality of this coarsening? I mean, you said that you're getting a compression, but you didn't give us any quantitative way to say what it was.
Correct. So I'm going to go back a second because that is going to come in, but sort of in the more technical part of the talk, but it's a great question and I would like to at least attempt to answer that right now. So if we did the compression in that way, then if I start with function f and apply this power of t, and then I discard that part of a spectrum that is small. That corresponds to throwing away frequencies of f that have gone below my threshold epsilon. And so the L2 distance between the left-hand side and what we're going to construct on the right-hand side is going to be in L2 of the graph smaller than epsilon. So that's our criterion for faithfulness and the only guarantee pretty much of the construction.
So this construction is naturally lossy then?
It's naturally lossy in the sense that at scale j, what we're going to lose is any information about objects which do not come by running the random walk at time 2 to the j plus 1, but maybe come from running it at a much smaller time scale so that they have fine structure that has not been killed yet by the random walk at that time scale. So think of running the random walk as smoothing out features of a function f. So if you start with an f which is very regular on the graph, applying t smoothes it out. The more you run the random walk, the smoother the object that you obtain. And so what we're going to lose at scale j are all the details that have been killed by running the random walk for time 2 to the j plus 1. No more, no less, actually. Exactly that amount of detail.
How's that compared to just like a low-rank approximation to the original matrix?
Exactly. So these are exactly low-rank approximations to the original matrix. There is a natural basis there, the basis of eigenvectors, but we don't want to use the basis of eigenvectors because the eigenvectors are typically non-local objects. And so if I were to compress the graph by using eigenvectors, I wouldn't have a good interpretation for the nodes of my compressed graphs. Each node would be like an eigenvector, and that's a global object. It doesn't preserve any local information about my original graph. Doing eigenvectors would be like doing Fourier analysis of a signal, where you use sine and cosine functions which are spread all over space. What I would like to do is analyze my graph and the functions on the graph by using localized functions on the graph. So if I get a large coefficient here, I know that something is happening here and not elsewhere. And so that's sort of the idea, replacing the basis of eigenvectors of these subspaces with a better basis. So it would be more like sparse PCA in a certain sense, if we were to make a comparison with PCA. Yes?
So are you manipulating graphs or functions over graphs?
I will be doing both. Right now, I like to keep the confusion. Both things will happen at the same time.
But you're not reducing the vertex set, right?
I will be reducing the vertex set.
So far, have you reduced the vertex set?
No, and I haven't told you yet even what the vertices of the new graph are going to be. Yeah, but we will be reducing them in the same way as these basis functions will be reduced. Yes?
Can you repeat what the axes are on the graph?
Oh, yeah, I'm sorry. So the x-axis is the index of the eigenvalues, and therefore of the eigenvectors of t. And the y-axis are the eigenvalues of t or t cubed or t to the sigma for me is the set of eigenvalues, the spectrum. And so when I look here, I say, well, there are 17 eigenvalues of t which are above 0.1. I could truncate here, and at every point on this axis, not only have the index of the eigenvalue, but I could think of having an eigenvector. And so I could define a space spanned by the eigenvectors phi1 to phi17. And there will be a subspace which is almost the rank of t if I discard everything which is below my precision 0.1. So these are exactly low rank approximations, but where I would like to have my basis vectors to be localized on the graph. So the way we're going to do that is the following. So we start with phi0. That's a basis made of delta functions on the graph. So every basis function in phi0 is just 0 everywhere and 1 at a certain vertex. This is a nice super localized set of basis functions for the graph. And we're going to apply to each of these delta functions the random walk once. So we apply the matrix T, and each of these delta functions is going to take one step of the random walk, and it's going to be like a little bump, little Gaussian bump if we want a time equal to 1. And that's what I call phi1 tilde. And then we look at the phi1 tilde, and we say, well, if we look at the Gramian matrix of these phi1 tildes, how does that look like? Well, the Gramian matrix, the phi1 tilde are simply the columns of T. So we know exactly what the Gramian matrix is like. And we know that the spectrum decays. And so we don't really need all the phi1 tildes to span the range of T. We can throw some of them out. And so we use an algorithm, which I will detail later on. It's essentially, for those of you familiar with the numerical side of these things, rank revealing QR factorization, to look at these bumps in phi1 tilde, discard the ones that are not needed to span up to epsilon the range of T, and keep only the ones that I need, and orthogonalize them. That's what I call phi1. So this step over here throws away some phi1 tildes, keeps the ones that are needed, and it locally orthonormalizes them. So phi1 now is an orthonormal basis for the range of T up to epsilon. So it has discarded part of the spectrum. So now we have t that goes from our original delta function basis to this new basis for the range. It's t again, except that the part of the spectrum of t below epsilon has been thrown away. So it's a rectangular matrix. Phi1 has a number of columns which is smaller than phi0. And so I can think of Phi1 as this new basis as sort of, well, both a new set of basis functions on the graph and a phenomenal set of basis functions on the graph. But I can also think of each of the columns as a new vertex in a graph. And, well, which edges should I pick on this graph? Well, on this graph, I could assign edges with weights given by t squared, represented on the basis of Phi1s. So t squared, Phi1, Phi1, so I use these indices to say this is the random walk t, but represented as a rectangular matrix mapping vectors represented with respect to Phi0 to vectors represented according to Phi1. So for sure, I can also consider the square matrix t squared, Phi1, Phi1. It's just two steps of the random walk as a linear operator, but represented with respect to my new smaller basis, Phi1. And so that's a square matrix which I can think of as being a weight matrix on the vertices of the graph given by the columns of Phi1. So this is a smaller graph, and we have a random walk on it, which is just t squared, just represented with respect to the new basis. Now when we apply t squared in this new basis to Phi1, we get Phi2 tildes. These are, again, bumps on the graph, which can get compressed. The ones that are not needed are thrown away, and the remaining ones are orthonormalized. And the procedure continues in this fashion. And at any stage, the diagonal steps, which are these compression steps, and combined with orthogonalization, are such that the new basis that you get spans up to epsilon the range of t to the j applied to the previous basis. So that this sort of guarantee about the subspaces being correct is preserved. And if you think about what we have done, we have used t as a dilation, which is one of the ingredients in the wavelet constructions. In wavelets, you start with a mother wavelet, a sort of template function, and you start dilating it. That's what the random walk is doing for us. And then in wavelets, you dilate by a factor of 2, and you throw every other wavelet out. That's a downsampling step where things get compressed. Well, in our case, the rule is not that simple. We're on a graph, so the compression is happening in these diagonal steps where only the necessary functions to span the effective range of the operator are being kept and orthogonalized to each other. And the phi j's that we construct, we think of them as scaling functions. They're like localized bumps on the graph. And there are fewer and fewer as we go up. So pictorially, what we've done is sort of going from the fine scale up. We start with the large graph with delta functions on it, and we've constructed coarser and coarser functions. And our graph as scale j is made as vertices given by the scaling functions, and edges whose strength is given by this operator t to the 2 to the j, maybe over here, represented on the corresponding basis. I'm going to write it down in the next slide. So the graph as scale j is made as vertices given by phi j, and there is a random walk on it, t sub j, which is nothing but the original random walk at time scale 2 to the j plus 1, represented in this basis. So if phi j has n sub j columns, then this is a small n sub j by n sub j matrix. And the guarantee that we had at the beginning is satisfied in the sense that if you start with a function f and you apply the random walk operator to it 2 to the j plus 1 times, you can obtain that by simply starting with your function f, projecting onto phi j, taking one step on that compressed graph, and then uncompressing. The L2 distance between the right-hand side and the left-hand side is less than something like j epsilon. And j goes from 1 to something like log n. Any questions about this? Yes?
Are the entries of T sub j guaranteed to be non-negative?
No. So the entries, so these are weird weights. Tj in general has both negative and positive entries, and all our consistencies are measured in L2. That's annoying and natural. I would like my phi j's to be non-negative and my tj to be raw stochastic. I think that if you impose those conditions, I mean, the problem is already kind of hard as is, and I think that imposing those SR constraints is quite hard. Albeit one of the directions in which we're going is a different direction where instead of doing sort of linear algebra type of thinking here, we are doing a sort of, we're thinking instead of random walks represented as matrices and their powers, really about compressing the stochastic process itself. And we're able to get then TJs which are actually again stochastic processes that turn out to be non-Markov but semi-Markov. But then as a probabilist I'm happier about that construction. This is work currently being done with Jonathan Mattingly. It's not out of publication yet. There's still quite a bit to do, but it's a construction which probabilistically I find much more satisfying. Yes?
So your chain is reversible, right?
The chain is reversible, yes, correct. Nothing would change for the directed case. Turns out that the algorithms that we use to do the compression and so on work without any trouble in the directed case.
Okay.
Yeah, so, right. And now I'm going to give you an example of how this computation is being run. So you can think that you can start with a function f on the original graph, so it can be rough and has all the details as the fine scale graph. And we can apply the compressed version of t to it. So now the result of this is a smaller vector, which is a function of the smaller graph phi1, and it corresponds to f having been diffused once. And then you can keep diffusing till scale j. And so you get f multiplied by a chain of compressed diffusions. And now the result is a very smooth function, but it's not being represented on the whole graph. It's represented on a much smaller graph, which has the size as equal to the number of columns of ej plus 1. So that's a representation of the result of applying this power of t to f. If you don't like the compressed representation, you can unpack it and get your function back. This is sort of so we know that this is a very smooth function, so we can represent it compactly, or we can interpolate it back without adding or losing any information back to the original basis. And so you can go back and sort of re-represent this result onto phi j, onto the previous basis. This is just a change of basis from a coarser basis to a finer basis. The function is not changing. These are all equalities up to epsilon. And you can go all the way back till you represent your result on the original basis. So here you have the result of a computation compressed, and you can uncompress it back. And there is only one point here where we're using reversibility, which is actually that we have explicit expression for this in terms of t itself. If t was not irreversible, there would be t transposes there. But that's all, actually. All right. So once you have done this compression scheme, you can do several things. You can compute t to the tf very quickly for all values of t. You can even compute the inverse of a Laplacian, or a weighted version thereof, like 1 minus gamma t inverse, by using this product formula that all involves binary powers of gamma t. These objects have all been compressed, and so you can compute that product, which of course is not really infinite, and you should always be working with f orthogonal to the kernel of that operator. You can apply it quickly. So let me show you some examples. So the simplest one is, of course, the circle. So this is a graph where every node is connected to the nearby nodes. And here are some scaling functions. So again, the input to the algorithm is just the adjacency matrix of the graph. It constructs the matrix T, and it takes in a parameter which is the approximation error epsilon, and then it spits out the whole multi-resolution analysis. So no ordering of the points, nothing, of course, matters to the algorithm except the precision parameter epsilon. So it outputs several scaling functions, several wavelet-like functions. These are going to coarser scales, and this is the coarsest scaling function of all. If you look at it, it's sort of half of this is sine or cosine function, which is the top eigenvector, but it's actually more localized than sine. It's 0 almost everywhere on half of the circle, and then it's non-zero on the other half. And the second scaling function will be 0 there and 1 here. So it's sparser than the eigenvectors themselves. And clearly those are sparser, but they still span similar subspaces. So you could look at that by doing sort of spectral diagrams. Every one of these matrices is the set of inner products between, so the PIs are the eigenvectors of the Laplacian and the index rows. So the index of the rows here is I. And the phi jk's are the scaling functions that we construct at scale j. And if you look at how they look spectrally, they look mostly localized in the low frequency bands. And then some of them look like wavelets. So if I look at a row here, this is telling me that these scaling functions over here are localized on the low frequency eigenfunctions. And then as we go up in the index of the scaling functions, they start spanning subspaces which are similar to the subspaces spanned by certain groups of continuous eigenvectors. So this is really doing a spectral decomposition of a matrix T going from low frequency to high frequency. And similarly, what happens with the wavelets. And the plots are going from finer scale to coarser scales. So the number of VJs gets smaller and smaller. Initially, we have quite a few, and then in the end, we only have a couple of scaling functions and wavelets. And you can look also at the matrix T being compressed. So the matrix T initially on the circle is a tri-diagonal. As we go up the scales, if we kept the matrix T with respect to the regional basis, it becomes less and less concentrated around the diagonal. But we're also compressing it. So our T's become fuller. All of these are in log scale, log 10 scale. So they become fuller but smaller. So the original one was 1,000 by 1,000. After a few scale, it's a 30 by 30 matrix. And by the end, it's a 1 by 1 matrix. So the way you can think of this also pictorially is that if you have a graph where every point is connected to the nearest points, and this is a geometric graph coming, for example, from a point cloud in 2D, what the algorithm is doing is creating sort of a set of multiscale landmarks on the data. Those are the red dots from fine to coarse scale. And it's creating edges, and these edges somehow summarize the strength of the random walk between the red dots. So for example, a single edge over here in the compressed graph, which now has very few vertices, the number of red dots in there, what is the weight over here is really the sum of all the probabilities on long paths of the regional random walk. So you can do this on any manifold. You just sample from the manifold, you connect every point to the nearest neighbors, and you get the multiscale analysis. We tried to do this also on text documents. So this is a different data set than the one that Ravi was showing earlier on this morning. It's just a simple data set of papers from Science News. There are about 1,000 papers. We start with a dictionary of about 10,000 words, and then we pick the words that appear meaningfully in this set of text documents. And it turns out that about 1,000 words are left. So unfortunately, this matrix looks almost like this if it's square, but it's not. Every column is a document, and every row is a word. And let's just put 0, 1, whether, to denote whether a word appears in a document or not. So you can embed these documents in low dimensions and color them by topic. We know the topic for these documents. Somebody read them all and categorized them. But you can also do a multiscale analysis on this document corpus, and you get scaling functions, which are like local clusters of documents, and you can look at the corresponding words. And so here are some examples, some of these scaling functions going from finer scale to coarser scales, being localized on certain topics, and then you can simply list the words which are more representative of those topics. All right, so just a few details, maybe 2 minutes, because I want to talk about dynamic graphs on the compression step. The compression step is achieved by what are called rank-revealing QR factorizations. So those are QR factorizations. So you write a matrix as the product of Q times R, where Q is an orthogonal matrix and R an upper triangular matrix. And in fact, you don't want to do this for the matrix T itself. You should be allowed to permute the columns of T. The column ordering has no meaning, so you should be able to permute them. And in these rank-revealing factorizations, well, if you had a full QR decomposition, it would look in this form. But if the spectrum of T is decaying, you can approximate that product by just looking Q11, assuming that R22 has small norm. So if the operator norm of R22 is more of an epsilon, you throw it away, and you approximate your matrix by a partial QR factorization. And now the columns of Q11 are what we're going to call our scaling functions when we compress T. So these would be the scaling function at scale 1. And R1, R2 is in a certain sense the operator T represented in the range with respect to the columns of Q1. And so this is the core algorithmic part. Remember that we would like our basis functions to be localized. In general, it's very hard to achieve sparse QR factorizations with the columns of Q nicely localized. And so that's something that we've done a lot of work on and we're still working on. Essentially, we combine existing rank-revealing QR factorizations with multiscale decompositions of the graph. So we decompose the graph in a multiscale fashion, and then we do these QR factorizations locally. That helps us computationally because we can parallelize things, and it also helps with the locality of the basis vectors. And we'll soon come out with a new paper where we do a new combination of these ideas, which is giving us great speed-ups even before parallelism. So in the original paper, we use a modified Gram-Schmidt QR factorization, which is sort of the only one which is really, which you can control a little bit, but it also gives you the rank revealing part, which is really important to have theoretical guarantees. We replace that by a combination of multiscale partitioning of the graph with the sparse QR algorithm by Tim David at the University of Florida, which is a multifrontal sparse QR, which is already amenable to parallelization, but it becomes even more amenable to parallelization thanks to multiscale decompositions. And so we are achieving good speedups. We still don't know whether the algorithm is going to be linear in n, or rather, I'm sure it's not for all graphs, but we would like to fully understand which graphs are such that the algorithm scales linearly in the number of vertices or edges.
Mauro, sorry,
Yes.
I'm confused about
Yes.
something. I mean,
Yeah.
the stuff that you were talking at the beginning, you weren't really talking about graphs. You were talking about linear operators. Right?
Essentially, yes, right? So what's the take home? When you start with a graph, immediately you say, well, the only thing I care about is actually the random walk on the graph.
Right.
Let's talk about compressing it.
And
We get the
this
basis
is my
functions
problem.
and we get these compressed graphs.
But in here now, you're really talking about graphs at some point. I mean, or at least on the computational part.
Well, so it's all about linear operators. The graphs come in where I say the following. So my compressed graph, Gj, is the set of basis functions that I got at state j of my algorithm.
Sure.
So I reinterpret these basis functions at vertices of the new graph, and I give you edges with these weights, such that if you run the random walk on this graph, you actually have this consistency property.
Right, but there's no difference if you have a 0 or if you have an epsilon somehow. Right, I mean, it's not that the sparsity pattern somehow, or if you really have an edge or not, doesn't matter. It's not combinatorial. Right, I mean,
What do you mean? So the edges are all inside T, and so we're using them all the time. And they affect the pattern of the compression scheme, of the VJs, of everything else.
The notion of locality is coming from the graph.
Yes.
right, but somehow, but I'm trying to understand in the algorithmic part.
The
Then you're
algorithmic
talking
part-
about using the combinatorial structure of the graph. You talk about cuts and
Correct. So there it's all looking at T, which has all the edge information, and so the cuts are done in a geometric way. Think of multiscale spectral partitioning. And the QR step also, when you build these basis functions, they're all constructed by looking at the columns of the matrix T, therefore they see all the edges and vertices and so on. So it's completely determined by the geometry of the graph. It's inside T. It's all encoded in T. And every step has to abide to whatever pattern these edges have around one vertex versus another.
Maybe if you look at what becomes an edge at level j, it might correspond to a path of length j.
Correct.
With some weight or something.
Correct, exactly. So the way you can think of the connections at scale j is that, well, this part of the graph has now been compressed to a node, this part of the graph has been compressed to a node, and there is only one edge with a funny weight. Well, what is that? Well, that is essentially saying there were many edges going from here to there. And let's look at the probability of taking any path of that length. Those paths have length about 2 to the j plus 1. And let's replace all of them by only one edge of the correct weight. So by taking random walks according to these weights on this much smaller graph, which now only has 1, 2, 3, 4, 5, 6 vertices, is the same thing as having random walked here for 2 to the whatever scale this was, steps. Does that make some sense?
Because of this Gram-Schmidt orthogonalization, so it's not really that it corresponds to a walk.
Well, so the matrices are not stochastic anymore. They do correspond to a walk in this weak L2 sense, in the sense that if you apply this power of the walk to a function, that's why I say weak sense, and you compare the results in L2, I would like to be able to do L1, then the results are close. But two things have messed up the probabilistic interpretation. L2 and testing on functions rather than, say, doing total variation distance between the teams or something.
Do your red dots correspond to a original vertex?
No. And the way I plotted them was actually by saying every vertex in the embedding had an x and y coordinate. Well, the x coordinate is a function on the graph. I can project it onto phi j, and I'm going to get a new coordinate for my red dot, the new x coordinate, and the same for the y coordinate. But they're new. They're not. There is a correspondence because we keep certain columns of T, which means that the red dots can be interpreted as coming from the original vertex set, and they're all included in each other. But I prefer to think of them as new vertices, which are local averages of the original ones, except that these averages are L2 averages rather than, again, true averages. All right, so in the 3 minutes that I have left, okay, well, so there's been a lot of work, especially in the last few years, about multiscale constructions on graphs. I think the original construction is due to Eric Kolachik and Mike Crovella, and where we take wavelets in 2D, we restrict them to a graph, which was sort of coming from the structure of the internet, large-scale structure of the internet in the US, and you receive these wavelets in 2D. Then we did the original construction diffusion of wavelets years ago with Rafi Kaufman at Yale. And more recently, there is a construction by Pierre Vandergeest and collaborators, which is a true graph construction, lives on the graph, is done on the spectral side of the graph. And there is a graph-like construction by Airoldi and Azari, which correspond to looking at all possible subgraphs of a certain size called graphlets and try to represent your graph as a linear combination of those. And even more recent work in a PDE setting by Osher and collaborators. And there are many trade-offs. You can ask, do these wavelets have the right spectral localization, spatial localization? Is there truly a multi-resolution analysis? Are the graphs being compressed as you go? And I think none of the algorithms does that except ours. Is there a fast transfer on these wavelets? And is the graph compression that is being achieved, if it's being achieved at all, sort of consistent in some sense? There is a lot of work to be done. Directed graphs, doing learning, and seeing how they fit with graph models in this multiscale setting. There are big algorithmic questions. When are the algorithms linear in time, linear with respect to the number of edges, for example, in the graph? There has been work by Yulu at Harvard on Heisenberg principles on graphs. How localized can you make these functions? Why they're both? How localized in space and frequency can you make these functions? And so on. So let me only tell you one thing about dynamic graphs. Okay, so we wanted to introduce notion of distances between weighted graphs, and the way we do that, I have one slide that I think communicates what the key idea is. We do the following. So if you can compress random walks, then you can think that you have a large matrix P. But you also have its siblings at different scales. So you have a matrix P for every scale J. Forget about the indices T and tau that I don't have to talk about. So you have such a decomposition for a graph at time maybe equal to 1, but maybe at time t equal to 2, the graph has changed, and you have, again, a sequence of matrices. Well, you can compare the matrices, you can compare them at the finest scale, or you can compare these matrices at any of the coarser scales. Well, of course, if you compare them at a very coarser scale, they contain very little information. They only contain the information at the largest scale of the graph. Maybe if the matrix is 2 by 2, it's only capturing the behavior of the top two singular values and eigenvalues and corresponding eigenvectors. If you go back down to the bottom scale, it contains all the information at the graph, but the graphs might have different number of edges, so it's not clear vertices, so it's not clear how to compare the two matrices, and they might be noisy. So you can think of representing each graph at every time step as a vector where every entry of the vector is an operator, and then introduce this feature vector as a representation of a graph, and introduce a norm on this vector, for example, by comparing the operator for the graph at time t, at scale j, with the corresponding operator at the same scale at time t plus 1. And you can use this as a notion of distance that incorporates information for the different scales. If you want to study coarse properties of a graph, you only look at this vector, feature vector at the coarser scales, but you can look at it at finer scale and finer locations. And just to give you an example, here is a graph that evolves in time. We built our own stochastic rules for evolving graphs in time. And only starting last year, actually, large data sets have come out. And so we're very excited about getting to analyze those. A data set was released by PNNL, and another one is going to be released next week by Los Alamos National Lab, where they have large networks of the order of hundreds of thousands and millions of nodes, respectively, that change in time. So that's network traffic on their own networks, anonymized, at least for Los Alamos. For PNNL, it's a synthetic data set. So we have a stochastic graph changing in time, and this is like a social network, so new vertices get added to the network, very few drop out. And whenever you add a vertex to a network, it draws an edge, and then more edges to the friends of the friend that it connected to. So these graphs tend to become denser and denser in time. And you can measure distances between these graphs as a function of time, that's the x-axis, at different scales. So this is the notion of distance at a coarse scale and the notion of distance at a fine scale. And for example, there's a situation where the distance at coarse scale is small and the distance at fine scale is large. Well, what does that correspond to? What happened there? Well, this is the graph at time t. This is the graph at time t plus 1. A new vertex got added to the graph, but its friends, it makes friends with a vertex here and a vertex there. But these vertices were already kind of close. So this is a change which is large for these two communities. A new friend has joined both of them. But it's not a change which is large at the coarser scale. So that's why the distance of the coarse scale is small and the distance of the fine scale is large. And there are cases where both distances are large at the coarse and fine scale. And that's a case where somebody joined the network, but he made friends with very far away parts of the network. And so that's a change which is large at all scales. So I'm going to finish by putting up a slide of questions. We did simulated network attacks and so on. And we are really looking forward to testing this on real data, which we have been missing for a long while. Thank you very much, and I'll take any more questions if there are.
Yeah, do you know the Gaussian free field on a graph?
Yes?
Okay, how is it related to your sort of multiscale decomposition? This seems like a very natural way to think about a graph in a multiscale.
I like the question. I have not thought about this. I don't know. Very interesting. Yeah, I never made the connection.
There's a reason to think actually that this is gives like even in fact like a tree-like representation of the graph where you get
Yeah, and I think that if we looked at the coefficients in this representation, it would be a multiscale representation of that field too, because the statistics of the coefficients would actually still look Gaussian.
Thank you very much.
Thank you.